Hi, it's Kyle with Just in Time, and in this video, we're going to be going over our device that we've called the IoT weigh scale. In today's video, we're going to be going over how the weigh scale works, but just before we go into the agenda, our team members are Farhad, myself, Ghostas, and Stefan. The agenda for today's video is we're going to go into the overview of why this item is needed for the restaurant industry. After, we're going to be then going into the weigh scale design, with Farhad going over the IBM Cloud IoT infrastructure, and then Stefan going over the Arduino code breakdown so that you can see what code we used and what changes we had to make to the code for the Arduino to work properly with our IoT device. After the design of how the front and the back end work, we'll then be going into the results and the analysis with myself. Number 4 is the lessons learned. Ghostas has been documenting over the time of our project of what problems we were running into and how we solved those problems using some online resources along the way. And then lastly, with myself, we're going to be going over the conclusion of what we plan to do with this technology in the future and what some internal dialogue that we'd like to share with you. So why do restaurants need to weigh their kitchen items? Well, in today's time, we all see that restaurants have it hard. There's lots of internal and external factors happening. And in the first 60% of restaurants, and within the first year, 60% fail. And within the first 5 years of their opening, 80% fail. Now, a lot of the big reasons that I saw in research from Ohio State University that we have detailed links to it in our final document is that they fail not because of bad reviews, but mainly from poorly run management. And so what we're looking to do is we're looking to introduce a device that they can put into their back storage areas so that they can weigh a lot of their solid and liquid items. We're looking to solve the problems for mid to large scale restaurants so that they're able to better forecast and waste less resources, and so that they can have a tighter supply logistics plan moving forward day to day, and again, waste less food. So how this IoT device works in the back end of, let's say, a storage room for a kitchen, the device works in using 3 steps. With a pen here, I'll go over the 3. Here's 1, here's 2, and here's 3. Let's just mark it here. 1, 2, 3. So the first thing here is that we have the scale. The scale will be something similar to like you have a scale in your bathroom. The scale would be at the, of course, at the below here. The load cells are so like this, and so these load cells are receiving the pressure from the item. Let's just call this item X. So it's receiving the pressure from item X, and this is the load cell here. And so it's receiving the pressure. This load cell then reports the pressure that it's receiving into what's called an amplifier. This amplifier is taking signals from the load cell and converting it into a format that the ESP32 takes and knows what to do with. Once this ESP32 receives this information, this data that's coming from the load cell, it's then outputting it to the closest gateway that is in the network. This Wi-Fi gateway is then taking this information and passing it over to the IBM Watson. IBM Watson will be taking the data that is streaming, let's say, every 2 seconds, and taking this data from this IoT device, let's say from item X, it's then outputting it into the front end for the managers at the headquarters to see actively how much grain they have for a particular item that they have left. So what I just discussed was the bullet points over here to the right. Let's clear this. And let's go here. let's pass this now over to the backend integration piece over to Farhad, and I'll be going into how the backend integration works from the ESP32 out into the internet over to IBM Watson.
Hello. So we have chosen IBM Cloud as our um, cloud service provider for instant notification whenever the weight goes up or below a certain value, and also live IoT data of the sensor for the weighing scale as well. So a few things are running here in parallel. We have used Node-RED to configure our flows. We have used the Cloud and Database, which is basically a Mongo database to store the data. And there's been a bunch of API integrations here as well. So if we look back at the Arduino code over here, so these are all the device IDs, and these are all the tokens and API keys that we have used over here. This is just for configuring the Wi-Fi that it connects to. And over here, as you can see, here is where the client ID and the authentication methods are all authenticated using the token that we have used before. So whenever the load cell is taking real data, it's being passed to the cloud. This is where the devices is connected. Here, if you can see, it says green, it is connected. Let's go look at the state right now, at the recent events. It is reading some data. We do have the prototype working right now. And if we put a bit of weight, it is in tandem with the weight that's being read and with the weight that's being passed over there. This is the actual weighing scale, which is just a UI where you can just see you're just putting on some weight and the weight's coming down. And this is the Node-RED flow. So basically, this module over here, the IBM IoT, was deprecated in the new Node-RED deployment. So we had to do a bit of research to go back into Git, and we found this over here, NPM, and we had to download the depreciated IBM IoT app into our Git repository, from our Git repository over here, load it up, and then after that we were able to see the IBM IoT palette over here. Usually from the palettes, once it's there, we can go over here and we can manage palettes, and you can search for it, and then you can install. Previously, it wasn't being able to even search. We weren't able to search either because it wasn't there in our repository. So over here, we have to put in the API key to configure which device it's going to take the data readings from. The function over here basically just states, take the data that's coming in from the ESP32 and just publish it. And then it says, just show in the IoT skill what that data is. We put a weight check function over here, where we have, for testing purpose, we've shown if the weight is more than 800 grams, send an email to farhad.faiz@gmail.com. So let's just try that out real quick and see how this notification works. So I'll have our thingy over here open, where I can just sort of just do this for a bit. Yep. All right, so here it says if weight is more than 800, send out an email. Let's see if we can get that going. All right, it's gone. It says it's sending. And as you can see over here in my email box, I've got a notification. Boom, message from Node-RED. This is the weight message that we're getting over here. And of course, the email notification can be customized as well. Thank you very much.
Well done, Farhad. Good job. So the results and analysis. We were able to, about 2 weeks before the deadline, we were able to successfully connect our load cell to the cloud service. 80% of this project was actually trying to get the device to connect to the internet. The other 20% was getting the weigh scale. This is the second bullet here, getting the weigh scale to update within the right amount of time and having it being accurate. And so on the left-hand side, you can see in the comments here, gets data from the load cell and the amplifier. This code here shows that that getting the update in a certain interval and getting it out accurately. How we were able to do this is that the code that was given wasn't fast enough, and the factor level wasn't accurate enough as well. So we were able to solve this by using a different library, the EX711 underscore ADC, and this allowed us get the job done because this used a different algorithm that you can see on the left that accurately pulled data from our load cell in real time. And this bullet here is showing a link for the front end for, because we're going over the results, we were able to then have a front end testing link that you can actively see how the weigh scale works. And this is an example here over on the left of it actively working. So this is the URL that you can see the front end for this. So now I'm going to be passing off to Stefan, and he's going to be going over the code breakdown of what code we used and what changes we needed to make for this project to work successfully.
Okay, hello, this is Stefan, and I'll be talking about our Arduino code, an overview of the different sections and what they do, some of the things we had to change, and some of the problems we encountered. Okay, so initially this file was the template for this file was created by a guy named Ant Elder and Henry Lacoste. Okay, so we only needed 3 libraries for our project. It's the Wi-Fi library, the PubSub client library, and the HX711 ADC library. So first we created an object from the HX711 ADC library with pins 14 and 12, 14 for data, 12 for clock. Also, something to note is in our reference material, it was cited to we were supposed to use the HX711 library, but we ran into some problems with calibrating and outputting the correct data. We would get we wouldn't be able to get a proper calibration factor, and the output would be okay until we get to past about 400 grams, and then the output became tens of thousands. So there was something strange going on there. So we opted to look for something else, and we found the ADC library, which does everything the original HX711 library does, but on a moving average with a rolling data set. Okay, and so this next section here, this is all to do with connecting to our API and our web server. These values here are given to us by the IBM Cloud Web Server when we register our device and create our profile. This is very important. We can see we're using token authentication. This is our token specifically for our device and the server that we are trying to connect to. Okay, and then we create another object called client, which is an object of the PubSub client library. This is what we're going to be using to push data to our web server. Okay, and then we create our variables for our SSID and passwords to get internet connectivity. Pretty standard. And begin our void setup. So we just we begin our serial monitor. With here, print some lines. We print saying we're about to connect to Wi-Fi. Here we begin our Wi-Fi with the SSID and password configured above. And then once we get connected, we print out Wi-Fi is connected with the IP address. Okay, and after that, we then begin our load cell. So we call the begin function on our cell, which is an object of the HX711 ADC library. And then after beginning the load cell, we need to put in some hard-coded values. One is the calibration, and one is the stabilizing time. So the calibration factor is actually quite important. This took us a long time, because most of the time spent on this project was trying to find the proper calibration factor and being able to output the data properly. And so after switching to the ADC library, everything became much more simpler. So if we pull up the calibration file on the HX711 ADC library, this file is used to calibrate our load cell with the HX711 amplifier, and it's very user friendly, and it goes step by step to show you how to connect or how to properly calibrate your load cell. All you need is an object with a known weight. I used my phone, which has a weight of 180 grams, and then I followed the steps and it spat out a number, and that number was 445.32. Also to note that we need a stabilizing time so we're not pulling data too quickly from our load cell. After we have those, we call the function start on our load cell. So that completes the initialization of our load cell. Now we get into our loop. This beginning section is just to say if we need to reconnect to the internet, if we lose connectivity. Secondly, we have the main part of our algorithm is what's used to pull data, the weight data from our load cell. So it's pretty simple. The most important part is this float I, which we're inputting our weight data. So we're calling this get data function onto our object cell and inputting that into I. These if statements are just precursors to allow us to make sure everything is ready so that we can pull the data. For example, we can see here we're calling cell update, and if update is true, then our variable new data ready becomes true. So basically saying that if there is new data, if we update it, that means there's new data to pull, so that becomes true, and then everything else follows. So again, important to note, I is where our actual data is being inputted. And then so if we look at the last section of our file, we have payload. Payload is what's being called it's what's being pushed to the web application, the API. And we can see we're incrementing it with I. So as I changes, as the weight changes, so does payload. So does payload, so does our web application will update as well with this, as long as payload, as there's connectivity and payload keeps changing, it will keep changing the web application. And then this next section is just to verify if the publish was successful or not. So if the client publish is good, if this is true, then we publish okay. If not, we do publish failed. That's more on our end to see if everything's working properly. And we can remember that client is a object of the pub/sub client. And lastly, this delay 200. Initially, this was 1,000, but it caused us some issues with not having real-time data. Initially, we commented it out and removed it entirely, but it was sending data too quickly, so we had to reduce it. And by trial and error, we found that 200 was the perfect spot where we get almost real-time and we're not overloading our server. And that completes the code overview. Thank you so much.
Thank you, Stefan, for enlightening us with the code breakdown on how the code is working and working with ESP32. I'll now pass it on to Ghostas, and he'll be going over the lessons learned from the very get-go of starting this project to getting this delivered and ready to go for our presentation, for our final.
Okay. I just want to talk about the problems and the issue we faced during this project and what we learned about that. The first issue was about reference. The reference we used for this project was so old. It was for 2018, and that's why we had some challenges. For example, in the material it said that they use ESP 8266 while we use ESP32. And also, because of that, finding the library codes was a little different, and it gets complicated. But After we figure out that, the next problem that we faced with that was about um, choosing the Arduino, Raspberry Pi, ESP32, or all together. So first of all, at first we decided to just use all of these three together, but after a while, because of our team budget and making the project a little simpler, so we decided to use only ESP32, which has all the functionality you need for this project. The next one was about the how to build this project. First we decided to build it very nicely, prepare the boot, and just make it fancy. But after a few weeks, we just decided to just show it. It works on the presentation day, and we make sure that it's useful and it works, so instead of showing it just only fancy and nice. So that's why we decided to buy some kits from the Amazon and try to combine all of our parts together and build this project instead of just trying to show it's really nice and fancy, but it's not work. During this project, I think the most important challenges we faced was about the how to calibrate our load cell, because we just tried a lots of library, different type of library, and it takes more than a week of us, our team, to figure out how to solve this problem, how to solve our calibration, because every time we tried with different code, we failed. But finally, we found a good library and code, and the combination of both together worked. And so the point we understand from that calibration was ESP32 is much more faster than Arduino board. And this is the reason that the calibration value of the load cell that worked for the Arduino and the other ESP32 didn't work for our project. And yeah, the last problem we faced was about the delay time. So delay time means that when we finish everything and we put the weight on our load cell, it takes time to show on the application that the weight is going up. And when we just pick up the weight, it takes a long time to go back to the zero. So that was one of our challenges. We just tried a few code, and by searching, we just figured out that in the code there is a part about the delay part, and the number is basically start with 1,000, and you have to play with that number. So we just changed that number to the zero. It didn't work, so we start to try the different numbers, and with different numbers we try and test the project to see which numbers work better. And finally we figure out that delay time should be 200. So it means that and it's worked very well. So when you put the 200 on the delays, when you put the weight on the load cell, it quickly responds, and the weight on the application shows that the weight goes up. And when you just remove that weight, it quickly back to the zero. This is all what we faced with the problems and the solution that we faced during this project. And yeah, that's it.
Well done, Ghost Task. Again, I can't really say anything more than my team is just rocking it tonight. They're killing it. So, for the conclusion and future directions with this technology, first, when we hit a benchmark of establishing a good foothold in the restaurant industry with mid to large scale restaurants, using this information and really solving issues in their business on how to really focus and mitigate certain problems when it comes to logistics and getting the right produce at certain levels. We're then looking to focus this technology on warehouses, at home, grocery stores, and in trucking. For example, in grocery stores, we can see this technology already moving in this direction. GE and Samsung both have fridges coming out now today that is actively allowing their users to see what they have in the fridge and how much. So the technology is definitely there. It's just that we're looking to focus on certain problems more for industrial type of clients. The second bullet, what we achieved in this project is that with our proof of concept is that we were able to get a device to weigh any object and display it on a web page anywhere. When I mean anywhere, a web page being able to access the internet anywhere in the world. We were also able to not just weigh an item, but when an item reached a certain threshold, it would then trigger an email and it would be notified to the user that a certain item has weighed at a certain X amount. And Farhad showed that in the video. And then lastly, taking this technology further in the restaurant vertical is that we'd like to test out with third-party resuppliers so that let's say Tesco is a very popular supplier for groceries at restaurants. So if this data could get into the hands of suppliers, that they could be using that data to then come in and restock. If that could happen, that would eliminate one major task for management and managers in restaurants of a thing that they don't have to do anymore. So those are the three things that I'd like to conclude with the future directions. And with that, I'd like to say thank you for watching this video and learning about how IoT devices could improve the life and for the business's vitality in the future. Thank you very much.